We can start now, sir.
Hello. Should I respond to the questions in the chat itself, or do you want me to respond live?
On live, you have to respond, sir.
Online, right?
Yes, sir.
All right. So, with regards to the first question, the question says, I listened to your video lecture properly and taking notes, sir. Though I face difficulty in answering the assignment questions, please suggest some ideas to answer the assignment problems, or where can I practice? Okay. So, at a very high level, the questions that, I mean, the stochastic approximation is an interdisciplinary topic. It relies on probability theory, ordinary differential equation ideas, and also ideas from real analysis, right? So with regards to assignment questions, my first suggestion would be to look at the textbooks that we followed for probability. For example, you could look at probability with martingales by David Williams, and that textbook has multiple questions as exercises, so you can practice some of them from there. With regards to ordinary differential equations, you could look at this textbook called as Dynamical Systems by Hirsch, Mail, and Devane. And that textbook, if I recall correctly, also has some exercises. You could do some of them. For real analysis, you could look at a textbook by Rudin, right? And there you should be able to find some exercises. Okay, so stochastic approximation is a very niche area, and the textbooks that are available, in particular the stochastic approximation textbook that has been written by Professor Borkar, unfortunately doesn't have any exercises. Is that okay? So it may be difficult for me to provide you with textbooks on stochastic approximation containing exercises. I hope that answers your query.
Sir, can you explain the difference between sigma algebra and Borel sets?
Sure. So, sigma algebra is defined for any set. Like if you have a set S, right, a collection of subsets of S forms a sigma algebra if it satisfies three properties, which is that it should include the parent space. Like if S is the parent space, then the sigma field should include that set S. It should be closed under complements, and it should be closed under countable unions. Is that okay? Now, one can show that if a sigma field satisfies these three properties, then it is also closed under finite unions, finite intersections, countable intersections, and so on and so forth. So any collection of any collection of subsets which satisfies these three properties, okay, that collection we will refer to it as a sigma field. Okay. Now a Borel sigma field, right, is a special instance of a sigma field. In particular, the Borel sigma field is defined in the context of the real line. So if you have a real line, right, I mean, I should perhaps correct my sentence. Borel sigma field, in some sense, is defined using open sets of a topological space. Is this okay? So in the context of real line, right, your open sets can typically be written as unions of open intervals, right? So you take all these sets find their intersections, their complements, their countable unions, countable intersections, and put all of them together. That collection together, which will also be a sigma field, is what is referred to as a Borel sigma field, right? And more generally, you can define this Borel sigma field for topological spaces, where again you take all possible open sets, take their complements, take their finite unions, finite intersections, countable unions, countable intersections, and or add all the missing sets, and together that collection will be referred to as the Borel sigma field. Does that answer your question, Baruch?
Sir, do you refer topological space by real number or area and volumes? Is it so?
So topological spaces, I'm not sure I get your question, right? So
Uh,
real line is an example of a topological space. Is this okay? But more generally, you could look at R2, R3, and in general RD. Those are all special examples of topological spaces.
Sir, what I want to ask is, what is the physical meaning of a d-dimensional space?
So an example of a d-dimensional space would be RD, right? And the physical interpretation is that in that d-dimensional space, you can find a basis that consists of d elements. So if you have a vector space which has d elements in the basis, then that vector space is said to be d-dimensional. An example of
Just
that would be RD, right?
exact. Actually, sir, I want to know what is the, I mean, where these are used. Generally, we use real number line, area, and volumes, right? But in textbook, d-dimensional space is referred for. Uh, then what is the physical meaning of that?
I see. See, I'm not sure I fully understand why you say that there is no physical interpretation, but often we may be interested in finding certain vectors of certain dimensions. Is that okay? So, to give you an example from reinforcement learning, is that okay? So, do you have some background of reinforcement learning?
Not exactly, sir, but I can, I mean, understand if you,
Okay, so let me try to give, at a very high level, some, application from a reinforcement learning perspective, right? So, in reinforcement learning, there is this notion of a policy or a strategy, right? So, you can imagine when you are playing chess, is that okay?
right?
So, when you are
Right,
playing
sir?
chess, you have a strategy which tells you, when you see a certain configuration of pieces on the chessboard, what move you will make. Do you agree? Right?
Agree, sir.
So that is what is known as a strategy. And in this now in reinforcement learning, what we try to do is we try to quantify how good a strategy is that okay?
Right,
To
sir.
how good a strategy is. Now, the way you quantify how good a strategy is in terms of what is known as the value function. Okay. Now this
Okay.
value function is actually a vector, and the
Right,
size of the vector is equal to the number of states and actions in your in the problem at hand. Is that okay? Like,
okay.
for example, in
Okay.
the context of chess, right, the number of states will correspond to the number of different configurations,
Right, sir.
and the quality of any policy will be a vector whose size equals this number of states and actions. Does that make sense?
Okay. Sir, kindly will you repeat it, sir, once again?
Can you repeat? You want me to repeat the answer again?
This line, the last line. After a strategy, what you, I mean,
So I'm saying that, in reinforcement learning, we would like to know how good a strategy is, right? And this
right,
is quantified by what is called as a value function.
right, sir.
And this value function is a vector whose size equals the size of the state space. Okay?
Okay.
So if the state space is very large, then this vector will be a very high dimensional vector. Is that okay?
Okay,
Right?
okay.
And often you use the stochastic approximation algorithms to find, for example, such vectors. Okay. So
Okay,
these
sir.
vectors, like for example, in this case, D, the little d that you are asking about, could equal the number of states in your state space. Okay.
Okay.
Does that answer your question about giving you a physical interpretation? Does that help?
Right, sir, right, sir.
Okay, and one can similarly see many examples where such vectors would be of use. I mean, more generally, if you think of optimization, is that okay? Right, often the
Okay, sir.
optimization could be over multiple variables. Is that okay?
Okay.
And we want to find one choice of these different variables. So together it will form a vector. Is that okay?
Okay.
Right? One
Okay. That is
vector could correspond to doing certain things in some axis. Another vector could correspond to doing things on another axis. Is that okay? Right?
okay. Okay, sir.
So if you have an optimization problem involving d choices to make, is that okay? Right? So that
Okay.
will
Okay.
be an optimization problem involving over d-dimensional space, and then you may, for whatever reason, have access only to noisy estimates of the function. Is that okay? So there, when you work with stochastic approximation, that will be an stochastic approximation algorithm in d dimensions. Is that okay?
Okay, sir. Okay.
All right. So Naman, is this question from you about this gate exam and data analytics?
Yes, sir.
Yeah. So the answer to this question is, see, if you want to do in reinforcement learning, like if you want to pursue a degree in reinforcement learning, I would ask you to, think about what exactly do you want to do, right? Reinforcement learning on one hand, involves significant empirical simulations, and on the other hand, it involves theoretical studies. Is that okay? Now, stochastic approximation on one hand can help you design lot of principled algorithms for reinforcement learning, right? For example, one can view this q learning algorithm, which is quite popular, right? Policy gradient methods, which are quite popular, right? And some extensions of those ideas. So one can, if you don't mind, can you mute yourself, because there is some background noise coming from your end, right? So the ideas of stochastic approximation can be used in the design of such algorithms, right? So if you want to be on the empirical side, a study of stochastic approximation will actually help you come up with principled ideas for designing algorithms, right? And on the other hand, if you are interested in theoretical analysis of reinforcement learning algorithms, like for example, why does q learning work, right? And what are the convergence rates of the algorithms, and so on and so forth. So in those situations also, knowledge of stochastic approximation will help. In fact, if you have a chance, and if you are interested, you can look at the Google Scholar profile of me, right? And there, if you sort of sort the papers by year, you will see multiple papers where we actually use stochastic approximation ideas for analysis of q learning, I mean, of reinforcement learning algorithms. Is that okay?
Yes, sir. Thank you, sir.
And you have also asked questions about textbooks or resources for further research in reinforcement learning. So I would again first ask you to, narrow down whether you want to go on the empirical side, or do you want to go on the theory side, right? Because the theoretical courses will, I mean, if you want to pursue theory, then my suggestion would be to strengthen your probability, statistics, optimization, right? Real analysis, those kind of things, linear algebra, for example. Whereas if you want to do, go on the empirical side, then you will have to you will have to familiarize yourself with ideas from deep learning. What are the different techniques that are available? How neural networks work, right? How machine learning algorithms work, and so on and so forth. And be aware of different scaling strategies, right? And so on and so forth. That okay? Like when you are in the empirical side, you are expected to be able to solve large scale problems, and you should have you should have a good knowledge and understanding of available techniques for being able to solve these large scale problems. Is that okay? Hmm?
Understood, sir. I have studied the reinforcement learning tools from the Stanford online and understood the techniques are used in the large scale system. I keen interest in pursuing my research.
either type your question in the chat box, right? Because I'm not able to follow you very clearly. Yeah, so Baroj, you have asked a question how to model stochastic approximation using Python, right? I mean, see, I'm not sure what exactly you mean by that. See, these are just update rules, right? So these are update rules, meaning if you have the nth estimate, how do you come up with the n plus 1th estimate, right? So these are like very I mean, there are like standard ways at any of the existing GitHub repositories, right? And whatever is your favorite algorithm, you can look it up, right? And those algorithms you can start modifying based on ideas that you are interested in, or the ones that we have discussed in class, and you can already do that. Is that okay? Right? I'm
Right,
not
sir.
sure if this is what you're looking for, right? So the way to
Right, sir.
get started would be to just like take any paper that of interest, perhaps the application that you have, and look at the GitHub associated GitHub repository, and you can download codes from there. Often these are publicly available. You download them, and you can start editing those codes, and running those codes and seeing performance and so on and so forth. Is that okay? Right?
Okay.
See, a specific example of stochastic approximation is SGD, right? Stochastic gradient descent. Okay. And like if you want to, for example, try out some ideas in reinforcement learning, then you can search for policy gradient methods. Is that okay? Policy gradient methods are special instances of stochastic gradient descent ideas. In fact, it is stochastic gradient ascent, right? So you can look up codes for those, and you can already run them. Is that okay? Hmm?
Okay, sir.
All right. Yeah, so again, there is someone by the name Dell. So you have also asked some questions about, problem solving related, right? So again, my answer to that is, see, the questions involve some understanding of ordinary differential equations, probability, right? Martingales, and some bit of real analysis and so on, right? So it may be a good idea to read a bit about this. I mean, the questions that we have been providing in the as part of assignments, and also that will be given as part of exam, will broadly be depending on the course that we have taught. Is that okay? So whatever concepts are there, I would suggest that you look up textbooks related to that. Like for example, for probability, you could look up the textbook of probability with martingales by David Williams, right? And for this ordinary differential equations, you could look at this Devane, Smale and Hirsch textbook on dynamical systems, and you there in each of these textbooks you will see problems at the end, right? And you can practice some of those problems. Is that okay? Hmm? Yeah, happy to help. So let me know if I can help you with additional questions.
So can you explain Suprema and Infima once again, although you have explained it in the course?
So again, what is your question? Can I explain supremum? Is that what you asked?
Yes, exactly, sir.
Yeah, so at a high level, the notion of supremum tries to generalize this idea of maximum. Is that okay? Right. So if I ask you what is the max between two numbers, it is like what is the max between 1 and 2? Of course, it is 2. What is the max between 3 and 4? The answer is 4. Right. So a max between a finite set of numbers is very easy to understand. Right. Now, if I ask you what is the max, let's say, of the elements in the open interval 0, 1, is that okay? Now, if I ask you this question, I mean, your answer would be 1, right? But then 1 does not belong to the open interval 0, 1, right? So that's where some discrepancy starts appearing, right? In the definition of max and the definition of, I mean, that's where the definition of max sort of starts facing limitation. Is that okay? right? So to answer this gap is where we bring in this idea of supremum. Is that okay? So towards supremum, what we think about, what we start with is this notion of an upper bound. Is that okay? So let's say you have a subset of the real line, right? Let's say the open interval 0 1. Okay, and then we say an upper bound for this subset of R is a number such that every element in this subset of interest for us is below this upper bound. Like for example, the open interval 0 1, right? For this set, I hope you agree that 2 is an upper bound, 3 is an upper bound, 4 is an upper bound, right? And 4 is an upper bound
Yeah.
because every element in
Sir,
0
for,
1 is below 4, right?
sir,
And
for that reason, one should be the upper bound,
yeah, so now supreme, so no, I am not sure I understood your question. So for the interval 0 1, right,
right?
4 is an upper bound. Do you agree? Every element in
Yeah,
the interval 0 1 is less than 4.
right, right, sir.
So an upper bound is a number which is bigger than every element in your set.
Right, sir.
Is that okay? Right? And now supremum is the smallest upper bound that you can find.
Okay, so in this case, one should be the smallest
Upper bound.
number. Yeah,
Yes, one should be the smallest upper bound. Is this okay?
right,
And
right, sir.
sort of don't insist that the supremum lie in the set itself.
Okay,
Is that okay? So that is in some sense a relaxation that we provide with. Similarly, the notion of inf can be defined, that is infimum. You find the greatest lower bound. Is that okay?
okay, okay, sir.
Right? And this idea can be generalized to arbitrary sets, right? Like for example, if I give you the the set of rational numbers, is that okay, between 0 and 1,
Okay,
right?
sir.
And similarly we can define this notion of an upper bound, and then we can talk about the least or the smallest upper bound, and that will be the supremum for this set as well. Is that okay?
Okay, sir.
All right. I don't know in what context you asked. I mean, there is this notion of lim soup and lim inf. Were you trying to ask the notion of soup in that context, or were you asking me from the perspective of stability of algorithms and so on? I'm not sure.
No, no, actually, I was asking in the context of, monotone convergence theorem.
Monotone convergence theorem. So where do you see a soup over there in monotone convergence theorem?
Actually, in the textbook, I follow singular Euler, and there I have seen this notion.
I see.
Even in Resnick Halliday, Sydney Resnick book that you have suggested in the classroom,
Yes.
even that contains the suprema and infima.
Yeah, yeah. So suprema and infima are there always, because I mean one has to keep in mind that lim sup and lim inf, right, are some of the key things that we use for studying limits of sequences, right? So lim sup
Right,
and
sir.
lim inf indeed involve within their definitions the notion of sup and inf. Hmm?
Right, sir.
All right.
Sir, actually, our problem increases when we see, union as well as intersection of suppose if you say for the definition of convergence concepts for random variable,
Mhm.
then we say, see in the textbook it is written as limit infimum of an where n tends to infinity is equal to union of n equal to 1 to infinity and followed by intersection of k equal to n to infinity ap.
Yeah,
Then
so one
actually,
has to be
yeah,
careful here, Baroj. Is that okay? A few seconds back, we were talking about limits of sequences of real numbers. Is this
right,
okay?
sir.
So there, the notion of supremum and infimum is different, right? But when we talk about limits of events, because you are talking of these unions and intersections, so these are only
Right,
set operations. Is this okay? So there is an analogous notion of supremum and infimum defined, right? Like for example, if you have a collection of events or set
right, sir.
subsets, right? So there, what we ask ourselves is, we look at an upper bound from a subset relation perspective. Is this okay? Like for example, if you had A and B, right? Can
Right?
you give me a set for which A is a subset of that set and B is a subset of that set? Is
Then
that
both of these should be equal.
no? A and B need not be equal. Let's say A and B are arbitrary sets. Is this okay?
No, but what you're asking, sir, is that A is a subset of B and B is a subset of A, then
I'm not
simultaneously they should be
insisting
equal.
that. I'm not insisting that. I'm saying let
Okay.
A and B be two arbitrary subsets of R, let's say. Okay.
Okay.
And now let's say I want to find an upper bound to both A and B.
Okay, then it should be the maximum, I mean, the
Now again,
of the,
see this upper bound here is not in a inequality relation. It is in a subset relation. Is this okay? So give me a subset of R. Okay.
okay,
Give me a subset, let's call it C. Give me a subset C of R such that A is a subset of C and B is a subset of C.
okay,
Okay, so can you think of a subset of C such that A is a subset of C and B is a subset of C, right?
right, right.
So for example, A union B could be one such example, right?
Ah, yes, sir. Yes, sir.
You agree? So if A is a subset of B and B is a subset of, sorry, A is a subset of R. Sorry, I
Hmm.
made a mistake. A is a subset of R and B is a subset of R. Is that
Right,
okay?
sir.
Like
Right,
for
sir.
example, A could be the open interval 0, 1, right?
Right, right.
Could be the open interval half to, let's say, 2, right?
Okay.
Now, can you give me a subset of R which, contains both A and B, right? So in
Yeah,
this
yeah.
example, you could take -5 to 5 as the open interval, and that would contain both A and B, right?
Right, sir.
But it you can see that it contains lot of additional elements which do not belong to A or B, right?
Right, sir.
-5
Right,
to 5. So then the smallest set which will contain both A and B would be A union B,
right, right, sir.
right? So in that sense, you can see that if you have a collection of subsets, let's say A1, A2, A3, and so on, right? Okay, a sequence of sets, then union of AIs, that will be the supremum.
Okay.
It's the smallest set which
Right, right,
of
right,
which
sir.
A1, A2, A3, all of them are subsets.
All of them are subset. Right, sir.
Is that okay? So then, from that perspective, one can now define lim-inf of sets. Like in your case, you talked about lim-inf AN. Is that
Right,
okay?
sir.
So lim-inf of AN, so if you think about lim-inf of AN will be union of intersections of AK, right? Where the union goes from n equals 1 to infinity and the intersection goes from k bigger than equal to n. Do you agree?
Right, right, sir. Right.
Right? So if you think of this intersection of AKs, okay, so if you think of
Mm-hmm.
intersection of AK for a fixed n, that is you look at intersection of AK for k bigger than equal to n, then as a function of n, so let's call bn, okay, b subscript n to be intersection AK k bigger than equal to n. Is that okay?
Right.
So bn as a function of n will be monotonically increasing, meaning in a subset relation wise, bn will be a subset of bn plus 1. Do you agree with that?
But how you concluded that it should be monotonically increasing?
Monotonically increasing in a subset sense. That is bn. What is bn? Can you
Okay,
help?
to get an intersection of that. That is what you are saying.
No, bn is an intersection an plus 1, intersection an plus 2, and so on. That is bn.
Oh,
Okay.
that's why the smallest should be the inter at least one element should be a subset of all of them. Right,
Yes. Yes.
sir? That is what you are saying.
One element should. I mean, I'm not
I mean,
sure.
the smallest one, suppose A1 is the smallest one, A1 is a subset of A2, that's why and A2 is a subset of A3, and so on and so forth.
Assuming that A1, A2 are subsets. Is this okay? A1, AN, A1, A2, A3, they are all arbitrary sets. Is this
Right,
okay?
right, right.
So A1 need not be a subset of A2 or vice versa. Let's say we have A1, A2, A3, arbitrary sets. Is this okay?
Okay,
Now let's
okay,
define Bn. Okay, like B1 would be intersection of A1, A2, A3, A4, all of them. Okay.
okay,
Now define B2 to be A2 intersection A3 intersection A4 and so on, right?
Right, right, right.
Notice that B2 is doesn't involve intersection with A1. Okay. And
Right, right,
similarly,
right.
you define B3 to be A3 intersection A4 intersection A5 and so on. So when you define it this way, one can see that B1, okay, is a
Mm-hmm.
subset of B2. Okay. B2 is
Okay.
a subset of B3 and so on. While A1, A2, A3 need not have any subset relation, once we define B1, B2, B3 the way I proposed, B1, B2, B3, they will be subsets.
Right, sir.
So in that sense, B1, B2, B3 have some monotone relation.
Yeah, yeah. That B1 series has the monotone relation. Right.
Exactly. Now, if you look at the smallest set containing B1, B2, B3, that will be the union of Bn's. Is this okay?
Okay.
So
Okay, sir.
that is what of AN is.
Okay, okay, sir.
All right. So those who are here, I mean, you could also give some feedback on the way I'm teaching course. Is it something that you are able to follow? If there are certain things that you are not able to follow, let me know. I can, try to incorporate them at least in the remaining 5 weeks of lectures that are there. Is that okay? So stochastic approximation is indeed an interdisciplinary topic. So, to understand it reasonably well, one would need a good background of ordinary differential equations, real analysis, probability optimization, and so on. So of course in one course it is not possible to provide all the background, but my aim and hope has been to provide a good overview of these topics, so that as and when things interest you, you can go into the details. Okay, so if you have any suggestions, comments, feedback about the course, please let me know that as well.
Sir, do you think if the stochastic approximation has application in stochastic calculus for finance as an area of discipline?
You said stochastic finance, is that what you said? Baroj, could you repeat, please? Is your question like, does stochastic approximation have applications in stochastic finance? Is that what you said?
Exactly, sir.
Yeah. See, as I told you, see, stochastic approximation is the name given to a family of techniques which include within itself stochastic gradient descent. Is that okay? Right?
Right, sir.
Stochastic gradient descent is something that is used everywhere, but in some sense it requires that the update rule be made up of only directions which can be expressed as gradient of some objective function. Is that okay? However,
Okay.
stochastic approximation also allows you to have update directions which cannot be expressed as gradients of some objective function. Okay, so in that sense it is very general. Okay,
Okay.
so to answer your question, see, of course it has applications in stochastic finance and other places as well. And the main advantage of working with stochastic approximation is that you need not have your hands tied. By that I mean, you don't have to say that my algorithm has to be of a stochastic gradient descent nature. Is that okay? Right? It can be actually much more flexible. So you can, often the way we design algorithms is we sort of look at a noiseless version of the problem under consideration. Okay. And then we look at a limiting ODE, which is deterministic in nature. Okay. And see if the limiting ODE will behave nicely. Is that okay? Right.
Okay.
And we use that limiting ODE to actually come up with stochastic approximation algorithms. Is that okay? And often your limiting ODE will be of the form x dot of t equals h of x. And this h often we may not be able to express as grad f of x.
Okay.
Does that make sense? Like h of x, in many situations, we won't be able to express it as grad f of x. So as an example, suppose I give you the ODE, x dot of t equals some vector b minus a times x of t. Is this okay? Right? Now, as you can see, b minus ax is a linear function in x. Right? So if I ask you, can you give me a function f such that b minus ax is grad f of x? Are you with me, Baruch?
Yes, sir.
So if I ask you, here is a function b minus ax, can you give me a function f whose gradient is b minus ax? Right? Okay.
Right.
If you think a bit about this, the natural answer you may think about is, okay, I should construct a quadratic objective function, right? And then use that as the parent function whose derivative is b minus ax. Does that make sense? Right?
Right, sir.
However, we would only be able to do such things if this matrix A is positive semi-definite. Is that
Right.
okay? And which
Right.
involves symmetry. Okay? That is, this matrix A should be symmetric. However, often in practice, this matrix A need not be symmetric. I mean, to give specific examples, if you look at policy evaluation with linear function approximation in reinforcement learning, there you will see that such matrices are not symmetric, and hence you won't be able to express b minus ax as a derivative of some objective function f. Is that okay? Right? So in such situations, you have to work with stochastic approximation. So if while I'm not an expert on stochastic finance, right, you would also be able to use such ideas directly in stochastic approximation context, stochastic finance context. Does that help?
Okay, sir.
Yeah, so Naman, you have asked a question about theoretical aspects of reinforcement learning, right? So my answer to that question would be that you look at I mean, you should start reading recent research papers that talk about the theory of reinforcement learning, right? I mean, to give some concrete thing, you could look at the Google Scholar profile of some of our papers, and from there, you should be able to find references to related papers. Okay, so that is something that you should already start doing, right? And if you want to get a good textbook on theoretical underpinnings of reinforcement learning, my suggestion would be to start with neurodynamic programming by Professor Bertsekas and Professor Sisiklis. That would be the starting point, because a lot of theoretical ideas, okay, their underpinnings actually come from this textbook. Okay, so neurodynamic programming and dynamic programming and optimal control, these are also some of the textbooks that we use to teach reinforcement learning within the Indian Institute of Science. Is that okay?
Understood. I am already following the Professor Bhatka's reinforcement learning course from the ASU University, sir, and
Okay.
I have some reference about that, sir.
Okay, so you already start reading research papers and these textbooks, right? And you have to bridge the gap that you have iteratively. That is, you start reading papers, figure out if there are some missing concepts about which you don't have a good understanding, and then you can refer to textbooks to fill in those gaps. Is that okay? Right?
Understood, sir.
All right.
Thank you, sir.
So I think there are a few more minutes available. If you have more questions, let me know. I'll be happy to answer them. Yeah, as I told you, if you want to provide some feedback about the course, that would, I think, this interaction session would be useful to provide such feedback and comments as well, so that I can incorporate it, and those who are going over the course, they could, be better benefited, so that, by me fine tuning the rest of the courses according to the needs. Hmm? All right. Thank you, Baruch. Yeah, let me know if there are any more questions. NPTEL team at ISC, let me know if this is a good place to stop, because I don't see any more questions. All right. Thanks everyone for joining. I hope you are getting benefited from this course. If you have more questions, I'm happy to help. If not, maybe this is a good place to stop. All the best, and best wishes for your future. Thank you.
Thank you.
Thank you.